Hello everyone, welcome to Technologies Discussion Channel. Today, I'd like to continue the discussion on filter design. This is actually the Part B series discussion. On Part 2 series discussion, I have discussed the 7 filter design specification. This is actually a continued video discussion on the Part 2 series discussion. On the Part 2 series discussion, as I mentioned earlier on, I have so-called discussed the 7 key parameters for filter design. This Part 3 series discussion, again, I'm going to continue the discussion on the rest of the filter design specification. This is very important. Without knowing the specification, we can't quantify the performance of the filter. So hence, all these 14 filter design parameters, they are very essential so as to quantify whether the filter performance meet your need or not. So basically this video, I will discuss what is actually insertion loss. Next will be on the VSWR, which is also return loss. We have various transfer function and response type. For example, we have Butterworth, we have Chebyshev, which I'm going to discuss on this. On the magnitude spec, for example, for some of the case, we actually allow ripple on the pass band or maybe ripple on the stop band. Basically, this will quantify how much ripple in terms of magnitude is allowed for the filter design. The number of order of filter, the larger the order, the larger the filter size. So hence, the better the performance also in terms of the skirt of the filter. So we are going to discuss this filter order also. Next will be on the phase linearity and group delay. Anything that we insert beside reduce the signal strength, we also reduce the delay. So we are going to take a close look on this parameter discussion. Last but not least, on the filter impedance. So we are going to discuss all these 7 in order to complete the full discussion on the filter design specification. This will be the Part 3 series discussion on filter design. So guys, if you're keen to know more about filter design, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on filter design. This is my email. If you have any question regards on this discussion, please drop me an email. Or if not, if you want to have a faster response, you are always welcome to ask me your question through the comment. Before I continue, again, I'd like to urge you guys to help this channel by like this video. When more you guys actually help to like this video will have a better chances to reach out to a larger audience. So guys, help me press the like button now. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. These are the first 7 series discussion on the filter design specification on the Part 2 series discussion. This video, I will continue from all the way from 8 all the way to 14. Let's start on the discussion on the first, which is the insertion loss. What is actually the insertion loss of a filter? In telecommunications, insertion loss is actually the loss of the signal power that is actually result from the insertion of a device, such as a bandpass filter, in between the transmission line, and it is usually expressed in decibel. What does this mean? For example, this is an amplifier, this is an antenna. We would like to put a filter in between the amplifier and antenna. You know that there is no ideal device. Basically, when you actually introduce a device, such as bandpass filter over here, you are going to anticipate some form of loss. For example, this is a bandpass filter. So even this is actually so-called the bandpass, but again, this subject to have some loss, which we classify them as insertion loss. So basically, insertion loss means that this signal is actually allowed to pass. However, due to the imperfect so-called device such as bandpass filter, you're going to introduce some form of loss, and we quantify this as insertion loss. And this insertion loss usually expressed in decibel. From here, you can see that in the ideal, it should be at 0. However, when we actually insert the bandpass filter, it actually dropped by minus 1 dB, as you can see from here. And therefore, we quantify the insertion loss as 1 dB. Okay, so don't confuse on this. So basically, this is on the insertion loss. Insertion loss is actually defined as the decrease in power delivered to the load when a filter is inserted between the source and the load. Okay, so basically you can see from this diagram here. Okay, for example, when we don't introduce the filter, let's say this is a filter. When we actually don't introduce the filter, we actually has this loop and we actually obtain the power, okay, from the first path here. So after that, we actually insert the filter, and again, we obtain the power. And from here, you can see that the definition of insertion loss is actually shown over here, which is 10 log. Okay, the power that you actually obtain, okay, without the filter. After that, the power that you actually obtain when you actually insert a filter in between the load and the source. So this is actually the definition of insertion loss. Insertion loss is actually due to dissipate loss, okay, which is associated with each reactive element within the filter, okay, which is the component Q. We also have some form of impedance mismatch. Okay, although we say that 50 and 50 ohm is actually matched, but how can you guarantee it will be so-called exactly 50? How about 50.1, 50.2? There is still some form of mismatch, and because of this, okay, you actually will have some form of insertion loss. Okay, so basically, this is so-called undesired. In the ideal world, we have an insertion loss of 0 dB, which is not practical in the reality world. Next will be on the VSWR and return loss. Okay, so VSWR actually stands for voltage standing wave ratio, and return loss, they actually both measure the same parameters, okay, which is the signal that is actually reflected back in a transmission line. Okay, so these have been discussed on the part one series discussion. What I mentioned on the part one series discussion, for example, when we actually want to have a band stop, okay, the signal or the incident wave will actually reflect back. Okay, so the more the signal actually reflected back, the less amount of energy will be able to pass through the filter, and the less amount of data will be actually appear at the output of the filter. Okay, so basically this is also very important for this VSWR for filter design. Okay, so basically how much can be reflected back, okay, which is the signal as mentioned here. So in short, VSWR is actually defined as the ratio of the maximum to the minimum voltage on a lossless transmission line. Okay, so again, if you're keen to know more about VSWR, I have done a so-called intensive discussion on VSWR on the transmission line. Okay, so this ratio actually represent in decibel and is actually called as return loss. Okay, so this is a formula, okay, for the input VSWR. Okay, but in the interest of time, I probably can't discuss this. Okay, so again, if you keen, okay, I can put the link, okay, for the discussion of VSWR for you to understand a little bit more on this VSWR and return loss. Okay, so what is VSWR and return loss? So this is what I discussed earlier on. When we actually has a perfect match, okay, let's say in the ideal world, okay, we have exactly 50 ohm. Okay, so the maximum power transfer actually occur. All the signal, okay, at the source will be able to pass to the load. So this is under the ideal world if we have exact impedance 50 ohm. However, as I mentioned that, okay, it may not be the case, and under some mismatch condition, let's say 50 to 75, beside 100% all sent to the load, some percentage only able to send to load, and some actually will be reflected back. Okay, the more that is actually reflected back, the lesser signal actually sent to the load, which means that it is less efficient. Okay, because most of them actually under this return loss, then I will actually has lesser so-called signal actually sent to the load. Okay, so basically this is for the VSWR and return loss. Okay, so this is another example here. Okay, you look at this waveform here. So when the signal actually hits, okay, from different medium, you can see that some actually reflected back, some will continue to propagate. You can see that the signal strength actually reduced for this case here, and this is also the amount of signal that is actually reflected back. Okay, so this is actually the return loss. Okay, so earlier on, most of the time we discussed about the S21. Okay, so return loss is actually the S11. Okay, which is the inverse relationship of insertion. For example, S21 over here. Okay, so basically this is the VSWR and return loss. Next, we are going to discuss on the transfer function and response type. Okay, so I will do another video to so-called to have a deeper discussion on this. But this one, I just want to quickly let you know that there are various so-called transfer function or response type. In short, okay, we have the Purcell, okay, which is the most gentle slope, as you can see from here. After that, we have this Butterworth. Okay, so basically Butterworth also has a gentle slope, which don't have any ripple at the pass band and also at the stop band. For Trebuchet, okay, we actually has two types. Okay, in short, they will have ripple in both the pass band and also the stop band. Okay, so last but not least, we have this ellipse. Okay, basically we have ripple, okay, at both the pass band and stop band. And the key advantage is they are going to have the sharpest transition. Okay, so basically you can see that they have the steeper skirt as compared to the rest. Okay, so again, I will do another video to discuss on this transfer function and response type. Okay, so beside that, okay, I also mentioned just now there will be ripple, okay, on both the pass band and also on the stop band. Okay, in some case here, okay, basically we need to quantify how much ripple we can tolerate. Okay, so basically we have this pass band ripple, we also have the stop band attenuation. Okay, so in short, some of the use case, for example, we don't allow many ripple on the pass band, and basically we want to quantify, okay, how much, okay, will be the ripple effect. Okay, so basically this is the maximum allowable variation in gain within the pass band. Okay, let's say 1 dB ripple. Okay, so we also have a stop band attenuation. We need to have the minimum required attenuation in the stop band. We can't have the effect of ripple. Okay, because the ripple actually has a maximum and minimum value, and because some of the stringent case, we want to ensure that at least we guarantee some form of minimal attenuation. So basically, these two will be so-called the value to quantify, okay, the performance on the ripple on both the pass band and also on the stop band. Next, we are going to discuss on the filter order. Okay, so if you still remember earlier on, I told you that the higher the order, okay, the more the steeper the slope. Okay, so basically this is an ideal filter. We know that this is not possible. So in order to make it more possible to the ideal world, we need to increase the order of the filter. As you can see that when the order of the filter actually increase, it becomes steeper. However, okay, you need to keep this in mind. The higher the order, the bigger the size of the antenna. Okay, so basically you need to have the trade-off, okay, in between the steepness of the skirt and also the size of the filter. Okay, so determine the steepness of the transition between the pass band and stop band. Okay, higher order means that sharper roll off, but more complex, okay, which means that they are actually much bigger in terms of the size. 13, okay, we talk about the phase linearity and also the group delay. Okay, let's start with the phase shift first. Okay, so phase shift actually refers to the displacement of two signals, okay, when propagate in a time domain. Okay, so this displacement can caused by a signal processing device such as amplifier or filter that performs certain operation on the signal, causing the output signal phase to shift from its original input signal phase. Okay, so let me put this into so-called words to understand better. Okay, for example, we have a signal that entering into the filter. Okay, as I mentioned earlier on, there is no perfect filter. Okay, for example, the phase actually has some form of shift. Okay, so basically this is what we know as the phase linearity or phase shift. Okay, basically when this signal enter the filter, it actually creates some form of phase shift. Okay, so the phase shift introduced by the filter is usually a function of frequency. In short, the different frequency actually will have different phase shift. Okay, so this is a quick definition on phase shift. Okay, so this is the standard phase shift. Okay, so in the ideal world, okay, we want the phase shift to be consistent, okay, on all the frequency. When we actually has this, it will be easier for us to so-called move back to the original signal here. However, this is not possible, and this is another ideal world that we actually have a linear phase shift. Okay, as you can see that this is predictable because it's linear. As you can see from here, the higher the frequency, okay, the phase shift actually reduce. Again, after that, when they meet into the F naught, they further reduce over here. Okay, so basically you can see that the different frequency actually will cause the different phase shift effect here. As I mentioned, this is under the ideal world, but in the practical world, you can see that we have this form. Okay, so it's less predictable, and this is actually the typical bandpass filter phase response here. Okay, so this is a definition for phase linearity. Let's come to the group delay. Okay, the group delay is actually the amount of time it actually takes for a signal, okay, for example, having a finite time duration, such as a pulse to go through a filter. Okay, as I mentioned earlier on, okay, beside, okay, when we actually has a signal going through the filter, for example, a bandpass filter, okay, beside having the insertion loss, you can imagine that the amount of delay also will be introduced to the signal. Okay, because you add in extra, okay, so-called device in between, for example, amplifier and antenna. Okay, this definitely will add to the delay the signal actually sent from the amplifier to the antenna. So this is what we mean by group delay. So the group delay is the amount of time, okay, that is actually take for a signal, okay, having a finite time duration, okay, such as a pulse to pass through a filter. And the formula to calculate the group delay is see over here, change in the phase and change in the frequency. Okay, so it is usually frequency dependent. Okay, as I mentioned earlier on, phase shift is actually depend on frequency. As you can see from the earlier on charts here, okay, you can see that different frequency actually has different phase shift. And because of this, we are going to anticipate also different group delay. Okay, so basically this is the equation to compute the group delay. Ideally, all frequency present in a signal should have the same time delay, okay, which means that all the signal at all the frequency, they should have the same delay. However, the signal will not, okay, for this case here, if let's say all the signal having the same frequency, they have the same delay, then the signal will not be distorted. Okay, however, narrowband signal, they are actually more likely to encounter constant group delay than signal having wide spectrum. Okay, so in the case of linear phase shift, okay, so you can see that this is actually consistent. So hence, I will be able to easily predict this, okay, because if you still remember, it's a slope and I will have a constant number. But however, in the actual world, the group delay may some fluctuation, which is unpredictable. So therefore, all the spectrum components are delayed equally, and therefore there's no distortion. Okay, if we have a constant group delay. Okay, phase linearity is the key to preserve signal fidelity and is actually very critical in some applications that use pulse signal. Okay, coming to the last parameters I'm going to discuss, okay, which is the filter impedance. Okay, for example, if we customize the design of a filter, okay, we can actually alter the so-called the impedance. However, when we actually alter the impedance, okay, please take note that when you actually do the measurement using the network analyzer, okay, this can be slightly challenging. Okay, let me come to this here. Filters are designed to sit in between a source and also a load. Okay, so basically you can see that filter which is sitting in between the source and also the load. In RF design, okay, so usually we have this ZS equals to ZL, which is 50 ohm. Okay, so we because when we actually design a filter, you know that they are going to join, for example, amplifier or antenna. And because of this, we actually do a so-called 50 ohm input and output port. So this actually allows the different device to be joined together. Okay, unless you're going to do a customized design all on your own, then you can join the amplifier at different impedance. However, if let's say you are going to sell this filter standalone, then you need to ensure that the impedance, okay, they are actually so-called 50 ohm, so that they are able to join, okay, to another company amplifier, okay, because the other company amplifier, they will also ensure that they are actually 50 ohm, so that they will not be having signal reflection when you actually join these two devices. Okay, if you still remember, as I mentioned earlier on, let's say we have ideal 50 and also 50 ohm, then we will not have reflected signal, and this is basically ideal. Okay, so this is what I mean. Okay, so therefore, to ensure maximum power transfer, we need to ensure that they are actually all 50 ohm. Okay, because we are going to join to another third party, let's say the amplifier, let's say the antenna. So because of this, we need to ensure that our filter impedance remain at 50 ohm. However, like I mentioned earlier on, you are always free to change your filter impedance if your amplifier is actually you are also designing. So you know your amplifier impedance, then you can actually design the filter to have the same impedance. And when they actually join together, they will still have the same desired performance. Okay, so let's say, okay, we don't have 50 ohm, then we can actually design the input matching network or the output matching network in order to let us to achieve this filter impedance here. So like I mentioned earlier on, okay, let's say we design filter network, okay, having a different impedance. okay, which is not 50 ohm, then we need to design this output matching network so as to achieve the overall to have this 50 ohm. Okay, so this is what I mentioned. If you have the design of an amplifier, you can actually go through the filter network, but we need to ensure that the impedance, they are actually matched. But if not, okay, let's say I'm going to sell this filter design, and I need to ensure that when we actually look into here, it must be 50 ohm. So therefore, this is on the filter impedance. Okay, in general, okay, Z in and Z out of the filter, let's say they are actually not always equal to 50 ohm. So therefore, in order to achieve this, we need to have matching network that commonly insert at both the input and output port so as to transform the input and output impedance to 50 ohm. Okay, so this will be the last parameters I'm going to discuss on filter design. Okay, so the first 7, okay, please take a look on the part 2 series discussion on filter design. So this video, I have discussed these 7 key parameters for filter design. With this, I'd like to end my discussion. Please help to like and subscribe to this channel. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you so much.